In this video, we're going to focus on limits of trigonometric functions. So to solve these kinds of limits, we can apply the same guidelines when solving or finding the limits of algebraic functions. Okay, recall that we can first try to substitute directly, right? If it results to a definite value, then that's the final answer. If it results to indeterminate forms like 0 over 0 and infinity over infinity, then we have to apply some techniques. Okay, and since we are dealing with trigonometric functions, we can simplify first using identities. Okay, so you have to review trigonometric identities. Another technique is to apply special trigonometric limits. Okay, we'll discuss these special trigonometric limits later on. All right, so apply them if they are applicable. Okay, one more thing. We will be solving these problems without the use of calculators. Okay, just in case calculators are not allowed during quizzes or exams or assessments. And also, since we are not using calculators, we will only be dealing with special angles. Okay, because we can solve for the trigo function values of special angles using the unit circle, right? So we have to familiarize ourselves with the unit circle. Okay, so you can memorize the entire unit circle if you can and if you want, or you can just memorize the first quadrant and the rest can be obtained using symmetry, right? And then you can use some other techniques, of course, like using the 45-45-90 triangle or the 30-60-90 triangle, whichever is applicable. And then we also have another method using the fingers, all right, that corresponds to trigo function values of the special angles. Okay, so you use whichever is comfortable for you, whichever you prefer. Okay, so let's solve some problems. First, we are asked to find the limit of sine squared x over cosine x as x approaches pi over 3. Okay, so again, this is the given. Let's try direct substitution. All right, we have sine squared of pi over 3. This is equivalent to the square of sine of pi over 3. Okay, so let's plug in the values. Sine pi over 3 is square root of 3 over 2 and it's squared. And then cosine of pi over 3 is 1/2. Just simplify, then you get the value of the limit. Okay. So next, we have limit of tangent 3 theta over secant of 2 theta minus sine of 4 theta as theta approaches pi over 12. Okay, so this is the given. Applying direct substitution and then simplifying, we get this expression: tangent of pi over 4 divided by secant of pi over 6 minus sine of pi over 3. Okay, and then we plug in the values. All right, so we have three special angles involved here: pi over 4, pi over 6, and pi over 3. Just evaluate their trigo values using the unit circle or using whatever method you prefer. Okay, so these are the values. Tangent of pi over 4 is 1, secant of pi over 6 is 2 over square root of 3, minus sine of pi over 3 is square root of 3 over 2. Okay, and then we simplify. So we have two fractions in the denominator. We can express the two fractions into a single fraction using LCD. Okay, then simplify further. Therefore, the limit is equal to 2 square root of 3. Next, let's try this one. We have limit of tangent of 2x divided by secant of 2x as x approaches pi over 4. Okay, again, this is our given. Applying direct substitution and simplifying, we get tangent of pi over 2 and or divided by secant of pi over 2. Okay, so let's plug in the values. Tangent of pi over 2, this is sine of pi over 2 over cosine of pi over 2. Sine of pi over 2 is 1, divided by cosine of pi over 2, which is 0. So we have 1 over 0 in the numerator. And then in the denominator, secant is reciprocal of cosine, so 1 over cosine pi over 2, where cosine pi over 2 is 0, so we still get 1 over 0. Okay, and both expressions are undefined, meaning they approach infinity. So we have infinity over infinity, that's an indeterminate, right? Since we have an indeterminate form, we can proceed to the next guideline where we apply some techniques. In this case, we can use identities. Alright, so let's simplify tangent of 2x over secant of 2x using their identities. Okay, so we know tangent is the ratio between sine and cosine, and secant is the reciprocal of cosine. Okay, so we can write the limit as sine of 2x over cosine of 2x. Again, this is equivalent to tangent of 2x all over 1 over cosine of 2x, because this is equivalent to secant of 2x. Okay, so we simplify. We can cancel out cosine of 2x so that we are left with sine of 2x. Okay, and then we apply direct substitution. Okay, so sine of 2 pi over 4, that's sine of pi over 2. Sine of pi over 2 is 1, therefore the limit is 1. Okay, next we have limit of sine of x times sine of 2x all over 1 minus cosine x as x approaches 0. Okay, so again, this is the given. Applying direct substitution, we get sine of 0 times sine of 2 times 0 is 0, so we have sine of 0 divided by 1 minus cosine of 0. Okay, sine of 0 is 0, therefore we have 0 in the numerator, and then in the denominator, cosine of 0 is 1, so 1 minus 1 is 0. So we have an indeterminate form, 0 over 0. Okay, so let's try to simplify using trigo identities. Okay, so we have sine of 2x here. We can use the double angle identity for sine. Okay, so sine of 2x is equivalent to 2 sine x cosine x. Okay, from the double angle identity. Okay, then we distribute sine of x, so we get 2 sine squared of x cosine of x divided by 1 minus cosine of x. If we evaluate at x equals 0, we still get an indeterminate in the form 0 over 0, because sine of 0 is 0, right? Cosine of 0 is 1, so 0 times 1, we have 0 in the numerator, and then 0 also in the denominator, because cosine of 0 is 1, 1 minus 1 is 0. It's still an indeterminate. Okay, so let's simplify further using another identity. In this case, we can replace sine squared x with its identity from the Pythagorean identity. Okay, so sine squared of x is equivalent to 1 minus cosine squared of x, and this expression is a difference of 2 squares, so we can factor, and the factors are 1 minus cos x and 1 plus cos x. We can now cancel 1 minus cos x, right? So that we are left with 2, 1 plus the quantity of 1 plus cos x times cos x, and then we apply direct substitution. Okay, so 2 times the quantity of 1 plus cosine of 0 times cosine of 0. Cosine of 0 again is 1, so we have 2 times 1 plus 1 plus, or times 1. Okay, therefore the limit is 4. Now, you might be wondering, how do we know when to apply identities for these kinds of problems, right? So, number one, of course, you need to be familiar with the identities. It really helps if you can memorize the different forms of the identities. And number two, most of the time we start with trial and error, okay? Just plug in the identities and see if it works, okay? And as you solve many problems, you will develop the skill that will allow you to recognize which identities will work for a particular problem. Okay, so just practice solving as many problems as you can. Okay, so next, recall that we have another technique to solve for trigonometries that result to indeterminate forms, right? We can apply special trigonometric limit theorems. Okay, we have two theorems. The first one is the limit of sine of u over u as u approaches 0. This is equal to 1. Okay, and then the next one, limit of 1 minus cosine of u over u as u approaches 0. This one is 0. Okay, alright, so we have a few ways to prove these theorems. The first limit can be proved using the squeeze theorem. So squeeze theorem. Okay, that's number one. We can also use the L'Hopital's rule for the two theorems. At this point, we have not yet discussed L'Hopital's rule. It is reserved for another video. Okay, or we can just simply plug in values for u that is very near 0. So you can put in 0.00001, okay, using your calculator, and see that it will result to 1 for the first limit and will result to or will approach 0 for the second limit. Okay, but basically these are the two theorems that we can use for the next few problems. Okay, so the question now is, how do we apply these theorems? Okay, so you just check the given limit if it follows or satisfies the form sine u over u or 1 minus cosine u over u, right? Just keep in mind, or just be sure that u is approaching 0 so that we can apply these theorems. Okay, so let's look at some problems. First, we have limit of sine of 3x over x as x approaches 0. Notice if we apply direct substitution, okay, we get sine of 0 over 0, where sine of 0 is 0. So the result is an indeterminate form, 0 over 0. Okay, now let's see if we can apply the special trigonometric theorems. Okay, for this particular problem, we can probably use the limit of sine u over u as u approaches 0 because we have a sine function, right? The problem here is that for this theorem to be applicable, the argument of sine should be the same as the expression in the denominator. Okay, so in this case, the argument of sine is 3x. Therefore, in order for this theorem to work, the denominator should be 3x. Okay, but in this case, it's only x. So what we can do, we can multiply 3 over 3 so that we can have 3x in the denominator. Okay, now why do we multiply 3 over 3, or basically any expression equivalent to 1? That is because when we manipulate expressions, we have to make sure that we do not change the original identity of the given expression. Okay, so in this case, we cannot simply multiply 3 in the denominator because it will entirely change the identity of the given expression. Okay, so we have to make sure that when we do something, we have to counter it or neutralize it. So in this case, if we divide by 3, we have to multiply by 3. So as you can see, this is just equivalent to 1, right? When an expression is multiplied to 1, the result is the same expression. So in essence, we did not change the identity of the original expression. Okay, so now what we need to do is group together x here and 3 in the denominator, so we can have 3x. Okay, and then just factor out the remaining 3. So we have 3 limit of sine 3x over 3x as x approaches 0. And then let's check if this limit satisfies the special trigonometric limit theorem. Okay, so what we need to do is let 3x be u. So what will happen is that this limit will become limit of sine of u, right? Because 3x is u, and then divided by u, again because 3x is u. Alright, now since u is 3x, if x is 0, then u is also 0. Therefore, u will approach 0. And so it satisfies the special trigo limit theorem. Okay, and if that's the case, then this is equivalent to 1. So we have 3 times 1. And so the limit is equal to 3. Next, let's find the limit of tangent of 4x over 3x as x approaches 0. So this is the given. Applying direct substitution, we get tangent of 0 over 3 times 0. Tangent of 0 is 0, right? Tangent of 0 is equivalent to sine of 0 over cosine of 0, where sine of 0 is 0, cosine of 0 is 1, so 0 divided by 1 is 0. That's the numerator, okay? And then for the denominator, we have 3 times 0, that's obviously equal to 0. So we have an indeterminate form, okay? Now, if you look at the two special trigo limit theorems, they involve sine and cosine, right? However, for this particular problem, we have tangent. So first, we have to apply identity for tangent. And tangent is the ratio between sine and cosine. So we can rewrite the limit as limit of sine of 4x over cosine of 4x all over 3x as x approaches 0. Okay? Now, it seems like we can use the first special limit, sine u over u, as u approaches 0 because we have sine function. However, the argument of the sine function is 4x, so it should be divided by 4x. We have 3x in this problem, so we can just multiply 4 over 4 and then switch 3 with 4 later on, right? So we have we can simplify first. Sine 4x divided by 3x times cosine of 4x, and then so that we can apply the first special trigo limit theorem, we have to multiply 4 over 4 so that we can get 4x in the denominator. Okay, so just switch 3 here with 4. Okay, and then you group together sine 4x over 4x, and then you group the remaining factors. So in this case, we have sine 4x, right, divided by 4x. So switch 4 and 3. So you can get 4x in the denominator as x approaches 0. And then the remaining factors are 4, right? And then in the denominator, we have 3 and cosine 4x. Okay, so applying the limit as x approaches 0, the first is equivalent to 1, right, according to the first special trigo limit theorem. And then for the second, we have 4 over 3. Cosine of 0 is 1. So this can be simplified as 4/3. Okay, so 1 times 4/3, the limit is 4/3. Okay, so last problem. We are asked to find the limit of 1 minus cosine x all over 4x squared as x approaches 0. Alright, so let's try direct substitution. So we get 1 minus cosine of 0 divided by 4 times the quantity of 0 squared. We know that cosine 0 is 1. So 1 minus 1 is 0. And then 4 times 0 squared, that's 0. So we have an indeterminate form. 0 divided by 0. Okay? Now, if you can notice, we can probably apply the second special limit. Okay? What's the second special limit? 1 minus cosine of u over u as u approaches 0, and it's equivalent to 0. Okay? So you just isolate 1 minus cos x over x in this case, right? So isolate 1 minus cos x over x, then you apply the limit as x approaches 0. And then the remaining factors, if you take out 1 minus cos x, so you have 1 in the numerator, and then in the denominator, if you take out x, then we will be left with 4x, right? And so we apply the limit as x approaches 0. So the first one, this is a special limit, and it's equivalent to 0, right? And then the second one, if we substitute 0, this will approach infinity. This is undefined, right? 1 over 4 times 0 is 0, so 1 over 0, that's undefined. Therefore, this value will approach infinity. And this is another type of indeterminate form. Okay, this is an indeterminate product, 0 times infinity. And if that's the case, then we have to find another way to solve this limit. Okay, now if you can notice, 1 minus cosine x is the conjugate of 1 plus cos x, right? And the product of these two expressions is 1 minus cosine squared x, and this is equivalent to sine squared x. So we now have a sine. We can probably use the first special limit, right? So let's try. First, we need to multiply an expression equivalent to 1, right? So in this case, an expression involving the conjugate of 1 minus cos x, which is 1 plus cos x. Alright, so in the numerator, we get 1 minus cosine squared x, which is equivalent to sine squared x. Okay, so we now have sine. Let's see if we can apply the first special limit. Now, the argument of sine in this case is x. Okay, so we just have to divide sine x by x so that we can apply the special limit theorem, the first special limit theorem, right? And then we have x here in the denominator, so there's no problem. And then since both of them are raised to the power of 2, we can just group these two expressions together and factor out the exponent. Okay, so the result will be in this form. Okay, so again, sine is raised to 2, x is also raised to 2, so we can factor out 2. Alright, and then the remaining factors, if we take out sine squared x, we'll be left with 1 in the numerator, and then in the denominator we'll be left with 4 and the quantity 1 plus cos x. Okay, so let's apply the limit. The first factor, we can apply the special limit theorem. Okay, so this will be equal to 1, so that's 1 squared. And then for the second factor, we have 1 divided by 4 times the quantity 1 plus cosine of 0, where cosine of 0 is 1. Okay, so this will become 1 over 4 times 1 plus 1. So 4 times 2, that's 8. This is 1 over 8. Therefore, the limit is 1 over 8.